Hey, let's talk about section 3.5, the derivatives of trigonometric functions. Um, uh, this section, I'm going to be a little less rigorous. I do have a QR code if you want something a little bit more substantial. Let's just talk about this in sort of a general way. I want you to imagine looking at the graph of y equals sine of x. And I'm going to say, well, what do you think the derivative graph looks like? So let's take this, look at this graphically. I want you to imagine the graph of sine, which starts at 0, and then at pi, it goes back to 0. At 2 pi, it goes back to 0. 3 pi, back to 0. Every single multiple of pi, it's back to 0. And sine looks like this, this, and if I make a mark here at negative pi, have this going on. All right, so that's y equals sine of x. That's what that graph looks like. Now let's go in green and say, well, what do we think the derivative graph looks like? Well, one thing I noticed that every single place where there's a horizontal tangent for the sine curve, that means the derivative would have to be 0. So horizontal tangent here, so the derivative graph would be 0, horizontal tangent there, 0, horizontal tangent there, 0. So first of all, so we've got all of these places that we know that the derivative curve for y prime, that they're going to have zeros there. Now, between these two zeros, I see that the slopes here are negative, and I think the estimate of the slope right here, that's where it's kind of steepest, that looks like it's -1. So I'm going to put a -1 there. I'm going to put that in for that curve. And then between this point and this point, the curve is increasing, and this looks like a slope of a +1. So let's say that here's +1, and all of the values of all the slopes there are positive. And then it starts decreasing again. And then maybe we see, oh, it's increasing from here to here. The sine curve is, that is, so therefore all the derivatives are positive, and it's kind of negative there. Now, what does that green curve look like? And the answer is, it looks like the cosine curve, because it is. All right? So we're going to say the derivative of sine is cosine. Okay? I'm not offering a rigorous proof here. I'm just saying it looks pretty obvious that it is. All right? So let's try this again. But now let's think about trying to show that the derivative of cosine is negative sine. So we'll start by drawing y equals cosine. And if you remember, y equals cosine, it starts at 1. And here at pi over 2, it's at 0. And at every odd multiple of pi over 2, it's 0. Pi over 2, and at negative pi over 2, and kind of goes and cosine then goes down. So it bottoms out here at pi, it's up here, tops out here at 2 pi, back down again. So there's your y equal cosine. Now, let's say, again, for the sake of argument, we don't know what this is. What would we say? We would say every place there's a horizontal tangent, the derivative graph is 0. Horizontal tangent, 0. Horizontal tangent, 0. Every place there's a horizontal tangent, the slope is 0 at that curve, and therefore the derivative has the value 0. Between these two spots, curve is decreasing. All of the tangent line slopes are negative. Looks like it's about 1 there. Sorry, -1 there. So let's go down to -1, increasing. And I think here is where it looks like about 1, so forth. And this is increasing there. So kind of looks like that. Now, it's not the sine curve. The black curve is not the sine curve, but that black curve looks like the exact opposite of the sine curve. The sine curve as if it was translated over the x-axis. And that is our not so rigorous proof that that the derivative of cosine is negative sine. I'm going to put boxes around this, and I'm going to double star this, meaning these are facts that we've shown, but you're going to want to memorize them. You're going to want to have no hesitation when you say, hey, what's the derivative of cosine? Negative sine. Boom. All right. And with that additional information, we can combine with other rules, like what's the derivative of sine over cosine minus 2? What is the derivative of sine over cosine of x minus 2? All right. And what do we think? Well, I see a fraction. I'm thinking the quotient rule. I'm going to remember that the quotient rule is that it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And again, I'm writing it out, but I'm going to repeat these words every time I do a quotient rule. I'm going to say bottom, and I'm going to write that bottom expression times the derivative of the top, derivative of sine, we just recognize as cosine, minus the top, which is sine, times the derivative of the bottom. The derivative of cosine x minus 2 is negative sine. And this is all over cosine x minus 2 squared. I suppose we could try to clean this up. I get cosine squared x minus 2 cosine x as I distribute that across those two terms. I get a plus from these two negatives, sine squared, all over cosine minus 2 squared. Wait, cosine, I need to write a black line there. I'm going to use the highlighter. Cosine squared plus sine squared. That looks familiar. I think that is one of our favorite identities. And that's so 1 minus 2 cosine x over cosine x minus 2 squared. And that's probably where we would leave that off. Okay, knowing these other facts allows us to do other problems. Let's try another one. It says weight hanging from a spring bobs up and down from a horizontal position, or up and down with the position function s is equal to 3 sine t. S is in meters, t is in seconds. So this thing is swinging, gosh, 3 meters, 6 meters at a time. Pretty crazy. What is the velocity and acceleration? Well, let's remember that if position is a function of time, the derivative with respect to time of position is velocity. The derivative of 3 sine t is 3 times the derivative of sine, which is cosine. And that's what velocity is. Well, what about acceleration? Acceleration is the derivative with respect to time of velocity, which in this case is the derivative with respect to time of 3 cosine t, and that's equal to 3 times negative sine of t, or negative 3 sine t. All right, just a quick note, we're given units, meters and seconds, so velocity is in meters per second, and acceleration in meters per second squared. By the way, we have the derivative of position is velocity, derivative with respect to time of position is velocity. Derivative of velocity with respect to time is acceleration. There's a third one, the derivative of acceleration with respect to time, or the third derivative of position with respect to time, is something called jerk. So if you want to find the jerk, you take the derivative with respect to time of acceleration, the derivative with respect to time of -3 sine t, and that is going to be -3 cosine t, and the units there, meters per second cubed. And that's measuring, again, how quickly acceleration is changing. All right. So, here are the two that we just talked about, sine and cosine. Derivative of sine is cosine, derivative of cosine is negative sine. Now we've got 4 other trig functions and their derivatives. It so happens that if we know the first 2 rules, we can derive the other rules. For example, let's take a look at the sine or tangent. I want to find out what the derivative of tangent is. Well, really, I want to find the derivative of tangent's alter ego sine over cosine. Well, in that form, it looks like I can apply the quotient rule. What was that quotient rule again? Bottom times the derivative of the top, derivative of sine is cosine, minus the top times the derivative of the bottom. The derivative of the bottom is minus sine, all over the bottom squared, cosine squared. So what do we have there? We've got cosine squared t, got a super plus here, plus sine squared t over cosine squared t. Oh wait, cosine squared plus sine squared, that's 1. Wait, 1 over cosine, that's an identity as well. That's secant. So 1 over cosine squared is secant squared. And that's exactly, I don't know why I switched from x's to t's. Let's put that back there. Do it all in t's, do it all in x's. It's all the same. And so we can show that that's a true statement. How many of these you're going to memorize? Well, let's just put double stars around this entire box. You're going to want to memorize all of them. Not that you can't drive them on the fly. It's just that in a time testing situation, you don't have time for that. All right. It says, find the lines that are tangent and normal to the graph of tan x over x at x equals 2 support graphic. All right. So let's handle the tangent line first. Hey, for the tangent line, I'm going to need 2 things, and that is a slope and a point. And what do I have? Oh, I have half a point. I know it's going to be 2 comma something. Well, 2 comma what? Well, how about 2 comma tan of 2 over 2? That's what I get when I put this 2 into that function. Now, what number is that? I don't know. Tan of 2 over 2, though, is a perfectly legitimate expression of a value. So we're just going to leave it just like that. All right, slope. How about the slope? Well, I think I'm going to have to find for the slope, I'm going to have to find f prime. This again looks like a quotient. So let's do the quotient rule mantra again. Bottom times the derivative of the top, and the derivative of tangent I've memorized is secant squared, not t, minus the top times the derivative of the bottom, which is 1. This is all over bottom squared. So what is f prime at 2? Well, it looks like it's 2 secant squared of 2 minus tan of 2 all over 2 squared. What is that value? No idea. But let's see if we can support graphically that this really is the slope of the tangent line, right? And my tangent line would be y equals, and remember our form for the point slope form, y1 plus m times quantity x minus x1, which in this case is going to be tan 2 over 2 plus this whole thing. Gosh, I kind of feel like I want to, actually going to want to put that value into a calculator. So let's go ahead, break out the calculator. Start a new document. I guess we're going to use the calculator page in this document, and I need the expression for, and I'm going to do this using some of this great calculator functionality. Control division gives me this great fraction. I think it was 2 secant, so times secant of x, and we don't put the subscript here, we put it at the end, subscript, okay, minus, oh, sorry, it's not supposed to be x, it's going to be 2, I think, plus tan of 2, and this was all over, I think, no, what was it? All over 2 squared, all over 4. All over 4. Okay. It gives us a expression. I want it in terms of numbers. Okay, 2.34094. 2.34094. 2.34094. Okay. 2.34094 times x minus 2. So we think that this is the representation of that tangent line. All right, let's go see if it ends up being true. Okay, I'll add a graphing page. I'm going to graph control, sorry, go back here, control division, and it was what? Tan of x over x. All right, making sure that my calculator is in radian mode. So there's our graph. Let's hit tab again. Let's go ahead and put in what we say is the that tangent line 2.34094 times quantity x minus 2. Parenthesis. Enter. Oh, that does not look like a tangent line. That does not look like a tangent line. Let's work backwards. 2. Oh, that's because I got the wrong y value for that point. Let me hit tab, tab it up arrow. Let me put a divide by 2 here. Let's see if that fixes the problem. Yeah, that looks much better. You know, you can see that that tangent line just kisses the curve at that one little spot, and that the tangent line has the same slope as the curve at that point. Great, we got half of this problem done. And that is, we know what the tangent line is. But what's this thing about a normal curve? A normal line. Well, you know, as we saw, we had this kind of curvy thing. Oh, I can't even draw it. Like that. And we have the tangent line, right? Well, a normal runs perpendicular to the tangent. So they form a right angle with the tangent line. Everything's the same about our solution. Tan 2 over 2, except instead of this number, we are going to use the negative reciprocal of that number, because slopes that are perpendicular to each other are negative reciprocals of each other. So if I were to just make that change to the slope, leaving the point with the point the same, I should get a normal curve. Let's give that a try. So I'm going to hit tab. And again, it was what? Tan of 2, close parenthesis, divided by 2. And now, instead of plus, it's now minus. And I'm going to put the 1 over 2.34094 There's my slope of the normal curve, and we'll multiply that by x minus 2. And hit enter. And indeed, those two curves look like they cross at a right angle. The black one is the normal, the red one is the tangent. Excellent. Alrighty. Last example looks like, yep, last example, y double prime if y is equal to secant of x. All right, let's start. I'm trying to use really good quotation here. If y is equal to secant of x, I can take the derivative with respect to x of both sides of the equation. It's a lot like algebra. All right, and I could write dy dx there, or I might write the simpler y prime. What is the derivative of secant of x? Well, you probably haven't memorized that yet. But let's go back up to this list up here, and let's see if there's some way, some tricks to help you memorize. Here's one trick. Ready? Sine, tangent, secant. They're all on one side. I put them all on one side for a reason, because this is cosine, cotangent, cosecant. Let me say that differently. Cosine, cotangent, and cosecant. All of my cos are over here, and they all start with negatives. So there's one thing that might help you memorize. The derivative of a co is a negative. Okay? Secondly, ready? Here's something I noticed a long time ago. Here's a tangent, and here's two secants. Here's a tangent, and here's two secants. Here's a cotangent, here's two cosecants. Here's a cotangent, and here's two cosecants. I want you to put together, there's always two secants, one tangent, two cosecants, one cotangent. So maybe we use that to say, oh, I know what the derivative of secant is. First of all, it's going to be positive because it's not a co, and it's going to be secant times tangent. Great. One step, right? Now I have y prime is equal to secant x times tangent x. Why did I leave that space? Because I'm going to take the derivative with respect to x of both sides of this. I get y prime. This looks like a product rule. What is that mantra for the product rule? First times derivative of second plus second times derivative of first. Okay, so let's call this the first. Let's call this the second. So first secant x, derivative of tangent. Remember, one tangent, two secants, that's going to be secant squared. Plus the second tangent times the derivative of the first, derivative of secant times tangent. So looks like my final answer here is secant cubed plus secant x times tan squared. Okay, and there's my second derivative. Okay, great. That concludes our lecture for section 3.4.